There's a common misconception that mathematics and science are difficult subjects that can only be mastered by a select group of students with special abilities. This is simply not true. We can actually teach more substantive mathematics and science than we currently are teaching, and in the process, make some of the most important ideas of mathematics and science accessible to all students. To do this, however, we need to rethink the goals of the mathematics and science curriculum. There's more to learning mathematics and science than memorizing facts and learning concepts and procedures. To really understand mathematics and science, students need to engage in the practices used by mathematicians and scientists. Unfortunately, these practices are not generally a focus of instruction, and as a consequence, they're not learned by most students. For the last 7 years, researchers at the National Center for Improving Student Learning in Mathematics and Science have been working together with classroom teachers to study how to engage students in 3 practices that are central to the work of mathematicians and scientists. These practices are modeling, generalization, and justification. Our research shows that students of all ages and abilities can learn these practices. Furthermore, by engaging in these practices, students learn the important unifying ideas of mathematics and science.
Collaborating with teachers over 7 years, researchers at the National Center for Mathematics and Science Education have studied the ways modeling, generalization, and justification strengthen students' learning of mathematics and science.
The model that we're going to be making today.
In this first and second grade class, students are modeling the function of a familiar form, the elbow.
A model that works like the real thing. They don't care if it looks like the real thing at all. They want to see if you can make a model that works like a part of your body. They want to find out if you can make a model that works like your elbow.
Before constructing their models, the students examine the movement of their elbows and select materials like pipe cleaners, paper strips, popsicle sticks, and cardboard tubing to build their models. At first, students working in pairs create hinged models that move freely back and forth. An important component of this process is sharing ideas with the class.
And how is it like an elbow? Why do you think it's like an elbow? Can anyone see one way that it isn't like an elbow, maybe? Sam?
Because it's bent the other way and our elbows.
Okay, our elbows are stuck right there.
The students investigate further the movement of the elbow and how it functions, restricting the motion of their own arms with the aid of rulers and masking tape.
You now bend your elbow backwards. I can do that. Oh, did her elbow bend?
No.
What's bending? She got it back a little bit, but what part's going backwards? Her elbow or her shoulder?
Shoulder.
Can you bend your elbow forward?
Yes.
Bends forward, okay. Can you bend it sideways?
Their models are then revised to function with a more limited range of motion.
It will break. What about, should we try it this way then? But then the other side will break, so. We're thinking of it, we just gotta try and figure out a way to get this side from going, bending. Because it works on it to keep this part healthy instead of bending backwards because it could with this part.
These 3 major components of modeling, construction, testing, and revising, guide work in other areas of science in many project classrooms. In a 3rd grade classroom, students move beyond physical models to descriptive models of patterns in data. While investigating their own questions about Wisconsin fast plant growth, students collect data on plant size and represent it on line graphs. They use these descriptive models of change over time to learn about patterns of plant growth. They also used their data and descriptive models to calculate and compare growth rates for the plant at different times in the life cycle. The students examined their line graphs from the first time they grew their plants. During the second round, They will compare their data to see if the pattern they observe here holds, if they can predict the pattern of growth for round 2.
That you're starting to see. Is there something similar? And ask, what do you mean when you say that, Michael?
It makes sense, but it goes up slow and then it goes up really high. Mine is not making that slow.
Peter, can you try to put some of your thinking into that?
Like when you just plant your banana plant, it'll start drying up slowly. But since it takes space to like have the flowers, it needs to grow pretty big, so it takes a big jump, and then it kind of it starts to slow down a little.
As the students plot the growth of their plants over the next month, they calculate and record the growth rate for the periods of time between data collection.
From day 9 to day 11.
Again, that's how many days?
2.
So that'll make it easy.
Okay.
But it was so day 9.
So we gotta get from 29 to 40 in 2 days. See, all you got is 11 right now. To 2 part 4 is 5.5. Yeah, it's 5.5. Good.
This 5th grade class also investigated growth, but used a different organism, the tobacco hornworm. They used graphs to model the differences in the patterns of growth for 2 groups of hornworms fed different diets. Here, students attempt to pinpoint a time in the life cycle when they observe early evidence of differences in the 2 groups. Using a series of frequency graphs highlighting variation in length, these 2 students explain when one group of hornworms, those fed a mixture called recipe, begins to separate from a second group fed green pepper.
You noticed was day 7 and day 9. Both they were bunched together. And day 15, they started to like break apart. Like the recipe was more over on the right side and green pepper was more on the left.
Ooh, you see that break even before day 20. You're starting to see evidence in day 15. There.
And then at day 20, it really started to break apart because
I can see where a person would look at the graph for 20 and say, this shows recipe eaters are bigger than pepper eaters. But if someone wanted to know when does this start happening, for you to say that it might even start as early as day 15 is really important. And I agree that goes in with which ones are growing better or bigger.
Modeling is again illustrated here, from collecting and representing data to sharing ideas. The students test and revise their models as they represent the data. In addition to building physical and descriptive models, scientists seek to explain natural phenomena. They create and use explanatory models to account for patterns that occur in the world. As students progress through middle school and high school, their scientific inquiry generally includes more attention to mechanism and causes. The scientific models illustrated in these high school classrooms are ideas or sets of ideas that explain causes of particular phenomena. A black box activity is used in this 9th grade class to introduce students to working as practicing scientists do. Each box has a funnel in the top inlet tube and a long outlet tube at the bottom. Students pour water into the funnel and observe that sometimes water flows out of the outlet tube and sometimes it does not. Their task is to work with classmates to develop an explanatory model for how the box works.
600 is the prediction.
Yeah, but it won't be. It'll be 400, I bet. There's no pattern. What is it? Is it 400? Oh, really? There is a pattern then.
So 400's coming out, and it doesn't seem to matter how much you're putting in. Is that what you guys are telling me? How much left?
Well, because it doesn't seem to matter how much is left in. Because right now there should be like 300 inside of here.
Okay.
And then if we add like 400 and then 100, then there would be 800 in the box. Only 400 comes out. So that, oh my God.
After spending several class periods collecting data and finding patterns in water input and output, each team of students develops an explanatory model based on their data and presents it to the class. Other students are encouraged to challenge and evaluate the model after the presentation.
We added 100 5 times and got 400 out. And then we added 400 and got none out, and then another 100 because with our model it says that with 500 water should come up. Then we did it one last time, we got 900 milliliters out.
At the end of the activity, students are not shown the mechanism inside the black box. Instead, the class evaluates and compares all proposed models in light of 3 criteria. Is the model consistent with the data? Does the model fit with the way they know the world to work? Can the model predict future results from the box? The class considers models adequate if they meet these 3 criteria. This experience with creating, evaluating, revising, and justifying models is a prelude to modeling in a range of scientific domains.
That has a hole in the bottom that lets it drain out. And so on every 5th time, the second beaker up here is filled up to 500. It can only hold up 500 so it don't sound. And so that's why you get 900. And it comes out.
How did you determine how much water you figured went into each tube in the water?
Because we figured that every time we added 400 and 100, every time we added 500, we were only getting 400 out. So we thought that 100 stayed in there. So it had to go to a different place than 400 did.
Oh, I see.
We're not quite sure on how it distributes.
The black box unit introduces techniques of scientific inquiry the students use in this course, exploring the relationship between the Earth, the Moon, and the Sun. In this classroom, students learn how the Earth, Moon, and Sun move relative to one another and use their knowledge to account for a variety of celestial phenomena. Using the skills developed in the black box activity, students examine data patterns and propose explanatory models for sunrise and sunset, phases of the moon, lunar and solar eclipses, and seasonal change. Students spend about 6 weeks investigating the Earth-Moon-Sun system, beginning with the question, why does the sun rise in the east and set in the west? Investigation of each phenomenon builds on the data from the previous one. Here, students demonstrate 2 competing models of a lunar eclipse.
Because if they're all in the same plane, then here would be a new moon and then it comes back, and here would be a full moon.
Okay.
So if you go around anywhere, it's not going to change.
Not going to change. Now we're going to have the moon orbiting in a 90-degree angle from the Earth orbit relative to the sun.
If this is the plane from the sun to the moon.
Okay.
Then
the sun to the Earth.
Sun to the Earth. Then this is 90 degrees. So the moon would orbit like this, and there wouldn't be any eclipses here. But when it went around, then there would be eclipses right here and right here. And if it kept going, there wouldn't be any here.
The final question of the course challenges students to propose and defend models to explain novel phenomena. The phases of the Earth as seen from Mars, for example.
Because the Earth and Mars orbit around the sun in opposite directions, which causes Mars and Earth to cross when it's new moon.
Collecting data, finding patterns, and explaining how those patterns occur are modeling practices freshmen learn in introductory courses. These practices are elaborated and refined in advanced courses, such as this genetics class. Here, students carry out scientific inquiry as they develop causal models and then revise those models in light of new data. The students are working with the software program Genetics Construction Kit to revise Mendel's simple dominance model to explain more complex patterns of inheritance. The class is divided into teams that work on problems involving 4 traits. Each of the traits differs in its inheritance pattern. The research teams hold meetings throughout the unit to share data and propose explanatory models. Each student records data, patterns, and tentative models in a research notebook. In the following video clip, you will see the result of several days of research on the part of one group working on the fruit fly trait body color, which is expressed in one of 4 variations: ebony, green, tan, and pallid. After collecting data from numerous crosses that they simulated using Genetics Construction Kit and wrestling with how they might change Mendel's model to explain those data, they propose and test a revised model. This model explains results that the simple dominance model could not.
Yeah. What did we breed, an ebony and a green?
Probably ebony and green, yeah.
You'd need so this could be ebony.
And then 1 and 3 has to be green, because that's what we bred.
Okay. 2, 2, 1, 3.
That's awesome.
1, 2, 1, 2.
2, 3.
2, 3, 2, 3. That fits too.
Yep.
Ebony and green.
So that's gotta be it.
Yeah.
Sweet.
Good job.
We figured it out.
Awesome.
We came up with this triangle theory, and we decided from the first couple crosses that we did that ebony was dominant and green was dominant, because when we bred ebony and ebony, we got ebony and pallid. So, and we got it in a 3-to-1 ratio, so we figured that ebony was dominant, just like green was dominant. So we used that in part of ours. But then we got some really weird crosses when we bred ebony and green. We ended up getting all 4 of them, and that's what this Punnett square is right here. So we figured out that green was a 2-3, and that ebony was a 1-2, and when we bred them, we ended up getting all 4 variations that fit on our model.
Where'd you come up with the 3? Why'd you add a 3?
Because there was no way that we could get 4 different color variations from just 2 alleles, because you only end up with 3 different combinations. So even if every single one of those was each a color, you still have one color that is coming from nowhere. So we came up with that maybe there was 3, but you only carried 2 of them. So you still can end up getting all different 4 color combinations from having 3 different alleles.
So what was the basic
The teacher reflects on the impact of this modeling approach to teaching science.
It's very powerful to watch students as they develop and test their conceptual models. They're not memorizing bits of scientific information given to them by a teacher, but rather they're developing realistic explanations for the data that they have collected. The students have ownership of those explanations and the deeper understanding that goes with having worked out an explanation rather than just memorizing one. Watching the students develop this rich understanding is profound. For example, the other day I was able to hand one student group a copy of a paper published by Nobel laureate Thomas Hunt Morgan. The conceptual model he presents in that paper is identical to the model that that group had developed.
So far, we have seen how these powerful practices, modeling, generalization, and justification, can look when teaching science. Now
As we have seen in these classrooms, focusing on modeling, generalization, and justification does not mean simply engaging students in different activities. It represents a fundamental shift in how teachers and students think about and learn mathematics and science. In particular, students apply what they know to generate new knowledge, rather than simply memorizing facts and procedures. Students are engaged in solving problems, rather than just drill and practice. Mathematics and science become languages for thought, rather than collections of facts and ways to get answers. We have presented an ambitious vision of mathematics and science classrooms, but our research shows that this vision is attainable.
The kids take so much more ownership of those ideas, and I noticed this throughout the year keep coming up. They remember, they think about, they talk about the astronomy knowledge that they learned during that time in ways that they don't about things that were sort of fed to them, because they were things that they came up with and they were really proud of themselves. And I think that's a really powerful thing about this curriculum, is that kids who sometimes aren't traditionally successful or whatever are all of a sudden going, I know why we see the same phase of the moon, and I can show you. Mm-hmm. And I think those moments are so fun and powerful and lasting.